Hi and welcome to Tutorial 5. In this tutorial, we'll introduce logistic regression and go over a practice analysis using data from the Western Collaborative Group study. We'll discuss how to interpret logistic regression output and calculate odds ratios with continuous and categorical variables, and how to estimate the log odds of an outcome. Remember that the type of regression analysis that we choose to conduct depends on our outcome. So far in the course, we focused on linear regression, where the outcome is continuous. Now we're going to turn to logistic regression, which is used when the outcome is binary or dichotomous. By binary, I mean that your outcome has two levels or categories. Often in epidemiology, this is an outcome that is yes versus no. So either you do or do not have the condition, disease, or symptom. Some examples include death, CHD, and high cholesterol, yes versus no. This is in contrast with linear regression, where we would model something like a continuous cholesterol level variable. Logistic regression is a form of generalized linear model. Generalized modeling means that we use some link function to link our nonlinear model to a linear model. With logistic regression, we use what's known as a logit link, also known as a logistic link or log of the odds. However, with logistic regression, the same general principles of linear regression apply. We still follow the same general process of building a model, interpreting coefficients, assessing confounding and effect modification, and examining assumptions. And you can also have descriptive, predictive, or effect size logistic regression models. But you'll recall that effect size models are the main focus of the course, because these are the most commonly used in health studies. Here's the basic code for logistic regression in R. The part of the code saying family equals binomial tells R that we are using logistic regression. These are the equations for both linear and logistic regression. With linear regression, we fit a line to estimate the conditional mean of y, the mean outcome, conditioned on the x's. With logistic regression, we try to do the same thing conceptually, but because our outcome is binary, 1 versus 0 or yes versus no, we're interested in the probability of y. For example, the probability of CHD for a given x value. Rather than model the probability of an outcome, we model the log odds. So with logistic regression, we are estimating the log odds of an outcome as a linear function of the x's. When we say logged, we mean ln, the natural log. P over 1 minus p in the equation means the odds. These are the same thing mathematically. So all of our estimates are interpreted as the log odds with logistic regression output. Recall from SPPH 400 and 502 that we can look at the odds of an outcome for a group, which equals p over 1 minus p, so the probability divided by 1 minus the probability. And the odds ratio is a ratio of the odds between groups. An odds ratio that's higher than 1 means the group of interest has a higher likelihood of the outcome compared to the reference group, whereas an odds ratio less than 1 means that the group of interest has a lower likelihood of the outcome compared to the reference group. As I mentioned, simple logistic regression is used when the outcome is binary, 1 versus 0 or yes versus no. There are extensions of logistic regression to handle outcome variables with more than two categories, like multinomial and ordinal regression, but we won't discuss these in this course. Like simple linear regression, we are not adjusting for other variables with simple logistic regression, and our explanatory variable can be either continuous or categorical. But we can also use multivariable logistic regression, which includes more than one explanatory variable. And the explanatory variables can be any mix of continuous or categorical variables. So let's say we have a binary outcome, like CHD, yes versus no, so 1 equals yes and 0 equals no. And our explanatory variable is age. So conceptually, we're interested in the probability of CHD for a given age. As you can see, those with CHD tend to be older, and those without CHD tend to be younger. When we have a binary outcome, we can't fit a linear regression model to estimate the probability of y, because if we try to fit a line for this data, we'll run into issues. The first issue is that if we fit a line to this data, the line could go above 1 or below 0, which doesn't make sense when we're modeling a probability that must be between 0 and 1. So it doesn't make sense to have a 120% probability or a negative 10% probability of an outcome, but these are values that we could possibly get when we try to fit a line to model the probability of an outcome. For example, we can see that if we try to fit a line to this data, those aged around 25 years and younger have a probability of CHD that's less than 0, while those over 70 have a probability that's greater than 1 or 100%, which doesn't make sense. You can't have more than a 100% chance of CHD or less than a 0% chance of CHD. The other issue is that the probability of the outcome does not increase linearly with our explanatory variable. Every additional increase in year is associated with a different increase in the probability of CHD, rather than this being constant like when we fit a line with linear regression. As you can see, there's more of an S-shaped curve to the probabilities. Every unit increase in X doesn't have the same increase in the probability of the outcome. So there isn't a consistent slope like we had with linear regression. There's a non-linear S-shaped relationship between age and the probability of CHD. So fitting a line isn't appropriate because it wouldn't accurately represent the relationship between X and Y. We could instead model the probability of Y as a logistic function of the X's. Without getting into the mathematical details, modeling the probability of Y as a logistic function of the X's using this formula will force our probability estimates to stay above 0 and below 1. And this would accurately represent the relationship between X and the probability of Y by modeling this relationship with the S-shaped logistic function. But we still run into the issue of each year increase in age being associated with a different probability of the outcome. The slope varies at different points across the function, so we don't have a constant slope to neatly summarize the relationship between X and Y like we did with linear regression. So we need to use the logit transformation to make this look like a linear function. This transformation allows us to model the log odds of the outcome as a linear function of the X's. Why do we want to look at the log odds? Modeling the log odds is better because it gets us on the scale of the linear function, so it allows us to fit a line. We want to get on the scale of the linear function because lines have nice, simple properties. A line has a slope, which has a simple, consistent interpretation. As I mentioned, with the initial S-shaped logistic function, the slope varied for different values of X. But using the logit transformation allows us to fit a line which has a constant slope that can be used to summarize the relationship between X and Y. So this allows us to boil down the relationship between X and Y to a single number, the slope. This slope tells us how the log odds of Y change with each increase in X, and this is consistent everywhere along the line. So rather than modeling the probability of the outcome as a logistic function of the X's, we use the logit transformation, which allows us to model the log odds as a linear function of the X's. Let's turn to sample data to better explain how we apply logistic regression and interpret output. The Western Collaborative Group study was a large epidemiologic study designed to investigate the association between behavior types and coronary heart disease, CHD. So the R script and data for this analysis are available on Connect. So let's start by looking at CHD by body weight. First, we'll create a binary variable for body weight for those greater than 170 pounds versus those less than 170 pounds. So less than 170 pounds will be the reference group. And then we'll fit a logistic regression model. How we interpret logistic regression output is very similar to linear regression, except that instead of modeling the mean of a continuous outcome, we're now looking at the log odds of a binary outcome. So let's look at the output using our binary weight variable as the explanatory variable and CHD, yes versus no, as the outcome. Here we can see that our intercept is negative 2.69. So how do you think that this would be interpreted? Remember that the reference category is those less than 170 pounds. We would interpret this as the log odds of CHD for those with a weight less than 170 pounds is negative 2.69. What about the coefficient for weight? How is this interpreted? This coefficient tells us the difference in the log odds of CHD between those greater than 170 pounds versus those less than 170 pounds, and is interpreted as the log odds of CHD is 0.53 higher for those greater than 170 pounds compared to those less than 170 pounds. Or we can also say that those over 170 pounds have a log odds of CHD 0.53 greater than those less than 170 pounds. What does the p-value associated with the weight coefficient tell us? Like with linear regression, this is a test of significance for the x variable. The null hypothesis is that the difference in the log odds of CHD between those greater than 170 pounds versus those less than 170 pounds equals 0. The alternative hypothesis is that this difference does not equal 0. So in this case, given that our p-value associated with the weight coefficient is less than 0.05, we reject the null hypothesis and have evidence to suggest that the difference in the log odds between those greater than 170 pounds versus those less than 170 pounds does not equal 0. What about the null deviance? The null deviance is similar to the sum of squared total in linear regression. So it's the error explained and unexplained by the model. It's the total variability. What about the residual deviance? This is also known as the model deviance and is equivalent to the sum of squared error, or the residual sum of squared, in linear regression. It's the unexplained variation, the amount of variation not explained by your model, or the error, or how far observed values deviate from expected values. So our coefficients in logistic regression output refer to the log odds of an outcome, but the log odds are not the most intuitive to understand. So we can instead calculate the odds ratio for a given x variable instead of discussing the change in the log odds. To do so, we simply exponentiate our beta 1 coefficient. This converts the log odds to an odds ratio. If we exponentiate the coefficient for weight, this gives us 1.70. How would we interpret this? This tells us that those who are greater than 170 pounds have 1.7 times the odds of CHD compared to those less than 170 pounds. Alternatively, we can say that the odds of CHD increase by 70% for those who weigh 170 pounds compared to those who weigh less than 170 pounds. To convert coefficients to odds ratios in R, you can either use the exponentiate or getOR function in the R code provided to get these in your output. What if the explanatory variable is continuous? So let's try a model treating body weight as a continuous variable. What does the intercept tell us in this case? In this case, the intercept tells us that the log odds of CHD when weight equals 0 is negative 4.21. What about the weight coefficient when we use a continuous weight variable? This tells us that for every 1 pound increase in weight, the log odds of CHD increases by 0.01. Notice that the value of the coefficient refers to the increase or decrease in log odds for each 1 unit increase in body weight. As a side note, remember when interpreting odds ratios, like on your assignments, if the odds ratio equals 2, the group of interest has 2 times the odds of the outcome compared to the reference group. It isn't correct to say that the odds of the outcome for the group of interest are 2 times higher than the odds of the reference group. Saying 2 times higher implies a 200% increase, which is equivalent to an odds ratio of 3. So an odds ratio of 2 actually represents a 100% increase in odds, or 1 times greater the odds. This is the same thing as saying that a group has 2 times the odds. This isn't true with the log of the odds. It's correct to say that the log odds of y increase or decrease with each unit increase in x. Or with a categorical variable, that the slope represents the difference in the log odds of the outcome of one group versus the other. What if we exponentiate beta 1 for our continuous weight variable? This gives us 1.01. So this gives us the odds ratio associated with each 1 pound increase in weight. So for every 1 pound increase in weight, the odds of CHD are 1.01 times the odds of those with a weight 1 pound lower. Or we can also say that every 1 pound increase in weight is associated with 1.01 times the odds of CHD. What if we wanted to compare the odds of CHD for someone who has a body weight of 200 pounds to someone with a body weight of 175 pounds? There's a 25-pound difference between 200 and 175 pounds. So we multiply this difference, 25, by beta 1, and this gives us 0.2605. If we exponentiate this, we get 1.3. So this means that those with a body weight of 200 pounds have 1.3 times the odds of CHD compared to those with a body weight of 175 pounds. Or we can say that the odds of CHD increase by 30% for those who weigh 200 pounds compared to those who weigh 175 pounds. What if your explanatory variable has multiple categories? So let's say that there are 4 weight groups, and less than 155 pounds is the reference category. Let's build a simple logistic model with this 4-level weight variable. What is the interpretation for each of the 4 weight categories? Remember, the reference group here is less than 155 pound group. So the intercept refers to the log odds of CHD for someone less than 155 pounds, the reference group. The interpretation of the intercept is therefore the log odds of CHD for someone less than 155 pounds is negative 2.94. Each of our interpretations for the other 3 categories are in relation to the reference group of less than 155 pounds. So for example, those with a weight between 170 to 182 pounds have a log odds of CHD that is 0.90 greater than those less than 155 pounds. To get the odds ratio for these, we simply exponentiate the coefficients. Remember, less than 155 pounds is our reference category. So we could then state, for example, that those in the 3rd weight category, so those between 170 to 182 pounds, have 2.47 times the odds of CHD than those who weigh less than 155 pounds. What if we wanted to instead compare those who are greater than 182 pounds to those who are between 155 and 170 pounds? So here we are comparing the 4th weight category to the 2nd weight category. To compare these groups, we simply subtract the beta associated with the 2nd weight category from the beta for the 4th weight category. So 0.648 minus 0.426 gives us 0.258. If we exponentiate this, we get an odds ratio of 1.29. This tells us that those who weigh greater than 182 pounds have 1.29 times the odds of CHD compared to those who weigh between 155 and 170 pounds. So we now know how to interpret the log odds and the odds ratio comparing one group to another. But what if we wanted to estimate the odds of an outcome? To do this, we use our logistic regression equation and simply plug in all the relevant values for our groups of interest. Let's take a look at our output with the binary weight variable. For an individual less than 170 pounds, which is the reference group here, we simply exponentiate the intercept of negative 2.78 to get 0.068. This tells us that the odds of CHD for those less than 170 pounds is 0.068. For an individual greater than 170 pounds, we add the intercept in beta 1 to get negative 2.15. And then we exponentiate this value to get 0.116. This tells us that the odds of CHD for those greater than 170 pounds is 0.12. So that's all I have for this week. In the next tutorial, we'll briefly review how to interpret the log odds and odds ratio and how to estimate the odds of an outcome. We'll also discuss the link between odds and probability and confounding, measures of predictive power, and effect modification in the context of logistic regression.
Thanks for watching our video. Stick around, guys, because we got lots more.